Well, hello everybody, and welcome to astronomy. We're going to look at Lab 1 measurements. This is right there. You click on that. It should take you to that assignment, and you might notice as I get here, as it's taking me there, I've got the due date at the top, and we're going to talk about some of the different things in there. Of course, basically what we're talking about here is being able to understand the size of things, how large things are, and be able to measure those things and convert those measurements as well. So having that and knowing that is going to allow us to be able to get a lot finished. When you go through the lab, you'll click on the drop downs here, and it'll give you the learning objectives to properly record measurements, convert them to various units, perform calculations using scientific notation, recognize and convert various angular units, and relate angular measurements to linear size through distance. And that's where we have some of the problems and things with this lab. In here, we need to look at not necessarily the miles per hour that we use here in the United States and a few other places, but the kilometer. We use kilometers and meters to be able to measure different things. In order for measurement to have any meaning, it must have a magnitude and a unit, and that unit in this case is going to be the meter. It says here, for example, if your neighbor had replied to how many units you measured, 1 hour, then 1 would be the magnitude and hour would be the unit. So 1 hour or 2 hours, you know what those things are. Well, here in this exercise, we'll be looking at different things, especially length and size. Now, we look here at a random galaxy. This galaxy says here it's inconvenient to use units of miles and things for this. Intergalactic units are measured in large distances such as light years or parsecs, while wavelengths are measured in such units as angstroms or nanometers. So we're talking about things that are very, very large, as this is, and the light that we look at, very, very small. For instance, a light year is, and that's thousands, millions, billions, trillion, 5,900,000,000,000 times larger than a mile. And an angstrom is 254 million times smaller than an inch. So we have all these different things we look at. Well, generally, we understand some distances here. A parsec, in this case, is the distance to a hypothetical star whose parallax is 1 second of arc. So if you look at 1 second of arc, okay, based on that 1 second of arc and how far we are from the sun, that 1 second of arc would mean that this star would be roughly 3.26 light years away. Now, what does that mean? What that means is if I'm looking at, say, this star I'm pointing at right here, okay, and I see that star today in June, for instance, say it's June, and I see that star again 6 months later, and it's moved just a little bit to the right or to the left. If that is 1 arc second, using the parallax, and if you take your thumb right now and hold it up over this dot right here and close one eye and then open the other eye, you'll see it shift. And that's what we're talking about there. That distance, 206,265 AUs, astronomical units, is what that is. And of course, the astronomical unit is 93 million miles, or 150 million kilometers. So as we look at that, and we look at the AU itself, and we see this parsec, this is a lot larger number for us to be able to use to be able to determine things. Normally with parallax and looking like that, you can only see things out about 50 parsecs, or 50 times 3.26 light years, because that's at that point the distance that it shifts is so small you can't really see it. We also have a light year. A light year is how far light travels in a year. It's not necessarily a time distance, a time length, but at a certain rate, 186,000 miles per second, or 300,000 kilometers per second, what you have is that distance covered in 1 year. So 300,000 kilometers per second times 60 seconds times 60 minutes times 24 hours times 365.25 years gives you a light year. In this case, it's roughly 63,000 AU, but we'll just say here it's exactly 63,239.7 AU. 63,000 is far enough. It's a long distance right there. All right, so here is your astronomical unit, roughly 150 million kilometers. Looking at this, 1.495979 times 10 to the 8th. If we move that back 8 places, you get roughly 149,579,900 kilometers in that. 1 kilometer is 1,000 meters. And the distance light travels in a vacuum, and this is in a vacuum here, is 1,299,792,458th of a second. That's also the meter is equal to 3.281 feet. Now a centimeter is 100th of a meter. If you have a ruler, you can see that because we have rulers that have meters and centimeters on those. Millimeter is 1,000th, a nanometer is 1 billionth, and angstrom is 10 billionth. So we have different things that correspond to different wavelengths. And the wavelength that we use for the visible light spectrum, which we'll learn about in chapter 5, 1 nanometer is the term that we use. But the visible wavelength is from 400 to 700 nanometers, or 1 billionth of a meter right there. So we do use these things. We just don't understand how they work all the time. Now, our unit conversion allows us to be able to convert from one unit to another. Starting off here, if we look at nickels in $25, all right? Well, first of all, we have to understand how this works. We first convert the dollars to quarters. The fact that 4 quarters equivalent to $1 can be written as $1 is 4 quarters, or 4 quarters is $1. Because both are equal to 1, it says there, the numerator and denominator are the same value in different given units. Now, to watch these examples in here, you have to press the play button. So we have $25, and then we take that times 4 quarters, giving us 4 over 1. So we actually clear out the dollars right there. And now we take that, and we take our quarters, 4 quarters, and there's 5 nickels. A quarter is 25 cents, and nickels are 5 cents, so there's 5 nickels in 1 quarter. So we take the quarter, and we break that down right there. And then we multiply all those things out, and it comes out to 500 nickels, when we can make that conversion from dollars to nickels. And there we are. $25, 4 quarters, dollars cancel, nickels, quarters cancel. So we're left with the nickels that we have multiplying 25 times 4, which is 100, times 5 is 500. All right, so we're going to reset that. Click the reset button right there. It goes back to the beginning. So how are we going to understand what's going on here? Well, let's take a look at the ski trip, okay? Now, this is a kind of a unit conversion that allows you to be able to convert the unit so you can actually see what's going on. Exercise 1, on a more earthly plane, let's first use unit conversion to establish a gasoline budget for a ski trip. We're going to take a trip. Not on our favorite rocket ship, but, we're taking a trip anyway. Follow the directions inside the instructive frame window and perform the calculation that follows. Each numbered tick mark on the ruler represents 1 centimeter. So this is 1 centimeter, 2, 3, 4. And notice when I put my cursor over top of that, I get the move icon right here. What you want to do is you want to take this icon here and you want to drag it up there to the starting point right here. Then if you press the shift key, you can take that and drag it up on the line so you can actually measure how many centimeters we're going from the start to the finish where we go here. Well, I know it's a little bit short, so got to kind of keep an eye right there. So we're at 10 centimeters right now. I'm going to take this and move it to right about there, and that gives us 12 centimeters. All right. So Now that you got the virtual distance in centimeters, and you know no trip is exactly a straight line, but you've got 1 virtual centimeter on the map corresponds to 39 actual miles in distance. All right, so we have 12 centimeters. I'm going to put a number right there, 12 centimeters. And then that corresponds to, again, remember what we did before, that's 39 miles that it says up here, listed in red, 39 miles. Your vehicle gets 21 miles to the gallon of gasoline, so we're going to go over here and put in 21, and our gasoline costs are $2.13 per gallon, 2.13. All right, so then we need to put in a number. That number right there, so we have 12 times, let me just get my calculator up here, see if I can get that up. And since we're going to be doing this, I'm going to use my scientific calculator. Hope I get this right. So 12, oh, clear, 12 times 39 gives me my mileage, 468 miles. And then, now this number's on the bottom, so then I will divide that by the miles per gallon I get is 21 miles and gives me 22.2857, blah, 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 blah. Okay, now that's how many gallons it's going to take me to be able to get there at that number of miles. So then, if I multiply that times 2.13, it gives me $47.46 dollars. So I'm going to put that in here. I'm going to put in 47.4, what was that number again? 468. How about $47.47? Because it wants us to round that. So that should be our answer for that that first section. Now, you do want to make sure and watch your rounding. You want to round like a number above 5. You want to round that up, and notice it saves those answers in there too. So it saved the answers in there, and now I'm going to move on down here to the next one, and it'll check that, and you get some points for doing those things. But just remember how we did it before. 12 miles or 12 centimeters times 39 miles gives you the mileage. Divide that by 21 miles per gallon of gasoline that our vehicle gets. Multiply that times $2.13 per gallon and gives you $47.47. All right. So here we have a Cepheid variable. And a Cepheid variable star is a star that the brightness varies in a specific periodic way. Over and over. So it just does this over and over. So if you look at it, it gets brighter, dimmer, brighter, dimmer. Well, how are we going to check that? Well, let's press play right here. And when we press play, notice you get peaks and valleys, peaks and valleys, peaks and valleys. Let's stop it right there. What you want to look at is from peak to peak. How far is it from peak to peak? Now, if I take this and move it again, you notice that 1 centimeter equals about 5 days. And that's what it says right there. Well, how far is it from this peak to that one? So let's take this. I'm going to put that right on that peak right there. And I'm going to look at it here. And it looks like about 2, you got to get really close to it. Not 2.5. A half would be right there. Maybe 2.3 centimeters. So let's just do this. 2.3 centimeters right there. So that means this thing peaks every 11.5 days. We do our data analysis right here, and it shows you 2.3 centimeters on the graph corresponds to 11.5 days. Wow, that's pretty good. So if we enter the length here of 2.3, then our days would be 11.5 right there. All right. Same thing right here. Now, the solar max happens every 11 years. It corresponds with solar storms and things like that. Looking at our star, you have a peak here. Every once in a while it peaks. The sunspots peak and then they dip and peak and dip and peak and dip. And right now we're on the upside of a peak right now. Maybe not as high as this, which would be really nice, as I'm a ham radio operator, but maybe as high as this. Still higher than the other ones. Okay? If we measure that, the distance between those peaks, bring this up here, and we can see here that this A to B is about 1/2 centimeter. So 1 centimeter, let's say here, 50 years is our, so 2.5 centimeters is actually 50 years. So half of that would be about 22 years. We'll just make that, because it's a little bit less. I have it not quite all the way on there. So it's about 22 years right there if you do half of that peak. Well, if I go up here and look at this, for 1 centimeter, that's 22 years, but I'm at 1/2 centimeter. So I'm at 0.5 centimeters times 22 years over a centimeter. The centimeters cancel, so half of 22 is 11 years. And that would be my answer. So, and actually that's right, because the sunspot cycle peaks every 11 years. So, what's this, the scale? Year per centimeter, that would be 22. And the average sunspot cycle peak is 11 years. And then I submit my answers, and hopefully I've got them right. Oh, that's right. Oh, that one's right. And then down here, oh, double check that you're entering the measurement in centimeters rather than multimeter. So I put that wrong. The scale on here is right there. I put 22. It should be there, the scale. So looking back up here, if I have my 50 years is 2.5 centimeters. If I go back over here and I go 50 divided by 2.5 gives me 20 years per centimeter. I put that in and check it, and it comes up as correct. All right, so moving on. Now, this is another part of, we're looking at large and small numbers, and this gets into your scientific notation. Looking at these large and small numbers here, when you look at the numbers that you have here, when expressed in scientific notation, the quantity has 3 parts. A number called a coefficient, a multiplication sign that follows a coefficient, and a power of 10 that follows a multiplication sign. For a number to be in proper scientific notation, the coefficient is always equal to or larger than 1, but smaller than 10. For example, instead of having to write 3 billion, you write 3 times 10 to the 9th. Where the decimal point is right here, we go 1, 2, 3, 4, 5, 6, 7, 8, 9. That gives us our 10 to the 9th right there. The second expression tells us that 3 is being multiplied by 9 10 times, and therefore it is 3 followed by 9 zeros. The power of 10 here, it says, is 10 to the 9th, and 9 is the exponent associated with that. So there is no reason you can't write 30 times 10 to the 8th. You still get 9 zeros, but this would not be scientific notation. Again, one advantage of sticking to scientific notation that always allows you to quickly rank 2 values that have different exponents. You're still going to look at numbers that are between 1 and 10. No number is going to be smaller than 1, no number larger than 10, with an exponent of, say, for instance, 9. So if you have 9.99 times 10 to the 9th is less than 1 times 10 to the 10th, because you have another 0 on there. So now looking at the numbers here, you want to check all the numbers that are following scientific notation. This one is not. There's no decimal point in there, and it should be between what? 1 and 10. This is 29. No, that wouldn't work. This one would work because it's a 1. This one would work. That wouldn't, because the decimal place should be there and it's over here. This wouldn't, and this actually would. So if you want to look at each one of those and you want to try to figure out what they are, then you can just select the ones that are between 1 and 10. Now here, this one needs to be moved, because if you take this and move it back with 0.035 times 10 to the 11th, you move that back 1, 2 places, that goes 11, 10, 9, 3.5 times 10 to the 9th. There you go. That's the number right there. Okay. So then you're going to pick these. Which one's largest? Which one's largest? So go work through those. And then you're going to convert here, scientific notation, which tells you how to go through and do that. So this actually shows you when you convert from that to standard notation, then you need to move your decimal places to the right or the left. Well, here, if I run this number 600,007, moving it to the places there to the right, it increases my decimal place here, moving it from there to there. If I want to go back the other way, there we go, right there. So this shows you how that works. So work on these numbers in there, and you can see that, and then you submit your answers to those. Now, the next section deals with angular measurements. This can be a little bit more difficult because you have a few more things to look at. When you look at even this picture right here, you see the awe-inspiring phenomenon of a total eclipse. This is August 2017. I actually got to see that on campus. There's the moon in front of the sun. The moon and the sun are relatively the same size or the same angular diameter. But we know that the sun's a lot larger, but the moon's also a lot closer. Therefore, even though the sun's diameter is 400 times larger than the moon, the sun is also 400 times further away, so you get this eclipse. Sometimes it can be a little closer. We're going to have an eclipse this coming week, where the moon's further out and you have what's called an annular eclipse, where you have a ring around the sun. But that happens every so often too. Now, these angles are what we use to be able to look at how everything is set up and how it works. So we're going to start off looking at the different angles inside here. First of all, you have a circle, which is 360 degrees. 1 degree is 1/360th of a circle. Then we break that down, that degree down, into 60 marks, which is an arc minute, which is 1/60th of a degree. And then we break it down again into the arc second, which is 1/60th of an arc minute. Now, remember what I said earlier about the parsec. This distance right here is how far a star would move if it were 1 parsec or 3.26 light years away from the Earth. You'd be able to see it move this much. Out to about 50 parsecs, you can measure that, but really we can't see anything further than that. So this is what it breaks down to look like. You have 1 degree, you have 1 arc minute, and you have 1 arc second. Basically, if we're looking at the sky, you can see those things as differences between one star and another. Now, there's 360 degrees in a circle, 21,600 arc minutes in a circle, and 1,296 arc seconds in a circle. Now, on the other end of the spectrum lies the radian. A radian is about 57 degrees. There are 2 pi radians in a circle. So if you take that and divide it out, the radian actually equals 57.3 degrees. Now what does that mean? Well, the radian comes from this line right here. From the dead center of the circle out to the edge is the radius, right there. If we take that radius and draw it along the circle, this becomes 1 radian right here, 57.3 degrees. All right? So we multiply that times 2 pi, and that gives us 360 degrees all the way around. All right? So conversion factors right here. 1 degree is 1/57th of a radian. 1 second, or 1 minute is 1/60th of a degree, and 1 second is 1/60th of an arc second, right there. So those are our conversions that we look at there. All right, so you take this and you're going to follow along and figure these things out right here. And this is not too difficult. I believe you can get that done. So looking at using this and going through here, pick the larger angular size by using these, and giving us the number of degrees that we have here, and you can figure out which one's the largest. All right. Then you can do your conversion right here. 14.3 degrees. To show you how this works, I would take 14.3 degrees and come up here, and where's my formula for that? Oh, there it is right there. So 14.3 degrees would go there. Let me see if I can do that here in the calculator. Let me pull that up. So it's 14.3 degrees divided by 57.3 gives me this much of a radian, almost a quarter of a radian. So I'd probably put 0.25 inside there. So there's your calculation for that. That's how you would do that. If I want to go from radians to minutes, then I would actually take that radian, convert it over to degrees, and then get that answer right there. All right, now, apparent size. We're going to be using a formula here that takes the apparent size of an object and figures about how far away it is, or the actual size of it. If you know the angular or apparent size of a distant object, and we know how far away it is, we can figure out the linear or actual size, S, which gives you the equation S equals R times A. Your R is going to be your distance right there to the object, distance to the object right there. The linear size right there, and then the angular size. You also have that. So the angular size right here. How many degrees wide is it? How far away is it? Giving you the size right there. Notice you put the cursor over top of the picture there. It actually shows you some different information there. So, looking at this, if we take an example of the moon right here, and the moon is approximately 1/2 a degree right there. If I take the degree right here and take the rad, divide it by that, it gives me 0.87 radians. So to do this, I'm going to go back to my calculator and clear that, and I'm going to take my degrees, which is it's a 1/2 a degree. So 0.5 degrees divided by 57.3 gives me the 0.00872 right there, or 0.0087, or 8.7 times 10 to the negative third rads. Okay, now we've got that in there, and the moon's average distance is, and again in kilometers, you want to use kilometers for this, is roughly 380,000 kilometers. So you take that, convert that over to 380,000. Well, I'm not going to do that. I'm going to take this number right here, since I've already got this in standard terms. Okay? I'm going to take that and I'm going to multiply that right here, because in my formula, I am actually multiplying the, go back up here, the R, which is the distance, times the angle, and this is my rads right here, times 300,000. Now 380,000. 380,000. That gives me roughly a distance here of 3,315 kilometers. That's how wide the moon actually is right there, which is pretty close to exactly right. So we did that, and we've gone through and gotten that information out of there. So we did that, and we got that number to show up. So we did the same thing here with Juanita's, and we're going to look at our different formulas that we have here. If we want to look at how the numbers work, rearranging that to solve for a number yields a few different equations. So when you look at the object, the closer an object is, the small r, the larger it will appear a large A. The larger an object is, a large S, the larger it will also appear a large A. So if I take this formula right here, that one right there, and I look at it, if I'm trying to find R or A, I'm just going to, if I'm trying to find A, I'm going to divide off whichever one that I want. So if I look here, I'm trying to find A. Where's my A? Right there it is. A right here divided by R. So A equals S divided by R. If I'm looking for R, I will divide A off of it, and I'll have S divided by A giving me my R. So I can find out how far things are away. And I can also find out the angular diameter of different things. So using that to calculate, you can come up with different information. So here is asking about Juanita's fingertip. And if you hold your fingertip out, take your left hand, hold your index finger out, that should be about 1 degree wide, okay? Well, Juanita's fingertips is about 1 centimeter wide, right there, okay? So if I take that 1 centimeter, let me clear this, and divide that by how long her arm is, or the length to the end of her arm, by 60, that gives me a number of 1.6, 0.016. I'm just going to leave it like that, okay? Now, if I take that and I multiply that times our radian number, which is 57.3. Where is that at on here? I want to show it to you again. 57, let me get back up here. 57.3, right there, 57 degrees. Multiply that times 57.3. That gives me an angle here of just about 1 degree. So there's your radian, and there is your degrees. So that's going to be actually 0.016 rads, and then now you have almost 1 degree on arm length. And most people's, and it shows here about 1 degree. So if you take that, put those in there, that should give you that answer. Now, this one is about the same. You need to calculate the angular diameter of Mars here, and then also convert that to apparent size units there, so you can get that, and then you'll submit that, and then you're finished with your assignment. This is not difficult. It is doable, And if you go through and put those things in, especially paying attention to this, you shouldn't have any problems with that. If you do have any problems or anything, you have questions, make sure to let me know. Again, remember, this is due by Saturday night. Thank you all so much, and I will see you next time. Thanks.